Hello everyone, myself Tellam Rambabu. Today I will explain one laboratory of digital signal processing lab. Our experiment is to implement FFT and IFT algorithms by using Arduino board. Let us discuss what is fast Fourier transform. In last lab I explained about a discrete Fourier transform, and for fast Fourier transform is nothing but it is an efficient way of calculating DFT. If you calculate a discrete Fourier transform by using traditional matrix method, you need to perform n square number of complex multiplications and n into n minus 1 complex additions to compute the DFT matrix, and after that you need to multiply that matrix with x of n. But if you use this fast Fourier transform, to use fast Fourier transform you need to maintain the size of the signal n equal to in general 2 power m. Here you can maintain n equal to some r power m, where r is radix and m is the power. Like here I am using radix equal to 2. If you maintain the length of the signal as 2 into 2 power m, then the number of complex multiplication you need to perform by using fast Fourier transform is just n by 2 into m, that is n by 2 into log n to the base 2. Number of complex additions is just n into m, that is n into log n base 2. This method is developed by the Attack and Cooley, their professors. I am not going to in detail. It has two types, two algorithms. One is decimalization in time, and decimalization in frequency. I am not going to explain the theory behind the fast Fourier transform, but our intuition is what I want to convey is the fast Fourier transform is a algorithm used to calculate the discrete Fourier transform in an efficient way. Okay, let us discuss about today's experiment. In this experiment we will find the respiration rate from the given ppg signal. That means we will have ppg signal, which in that frequency ppg signal only respiration signals is also there. So in general this is the frequency range of respiration signal, 0.05 Hz to 0.5 Hz. By using this range we will find the frequency of our respiration signal. So after applying the FFT to my signal, I will have many coefficients now. So I need to search in the coefficients which will give this, and for this is a coefficient range. F into n means number of signal, or dn point dft by fs. If I use f equal to 0.05, I will get one value, and f equal to 0.5, I will get another value, like let's say k1 and k2 respectively. So I need to search, I need to find the coefficient in FFT representation in between k1 and k2, and I need to find the maximum value in between the k1 and k2, and I will find that corresponding frequency. Why we are finding? Because our frequency range of respiration signal lies between here only, so there is no need to search in the other range. That's why we'll search here only, and after that we'll compare that with only respiration signal. We have only respiration signal, and we will find the FFT of that respiration signal, and we will find the frequency by using by using same method what we did in last week, and we'll compare the both. So I will explain code later, but let us see the FFT. This is the FFT what we will get for the input of PPG plus respiration. If you give input PPG plus respiration signal, and now if you compute the FFT, that will looks like here. This is the frequency corresponding to ppg, but we need, as I mentioned earlier, that the respiration frequency is low component, so we need to compute this frequency. I think this frequency, like that, between which lies between, we'll take k1 and k2 range according to previous formula. According to this formula we will find k1 and k2, and we will search in those window to find the maximum frequency component, and we will find the frequency. And this is the frequency response for only respiration signal. Like this is only respiration signal means this is the corresponding frequency. So in that signal you need to find this corresponding coefficient, and we need to compute respiration rate. And after finding the respiration frequency from this, and we will make other frequency components 0, and we will apply inverse Fourier transform to get the x of n. This is what I got. This is what I will show again. This is what I got, and this is actual respiration. But here the shape may be somewhat different because we will plot to somewhat only real components only, but the respiration will see how respiration will vary. So let us go to Arduino codes. Okay, in that Arduino code, basically what we'll do is, like, my signal length is not 2 power m, so I'll add some zeros. Zero padding do not affect the frequency response, but it will increase frequency resolution only. So this is my input signal, like this is my ppg VReal is my ppg signal, which includes some zeros. So I'm taking the imaginary part of my signal is 0. So since I need to use the FFT is the inbuilt command in Arduino. To use FFT you need to include this include Arduino fft.h. And now my sampling frequency is 25 Hz only. This do not require actually. And to find the maximum frequency component, I'm using m and maximum. Okay, here BP is in the sense of breaths per minute, breaths per minute, like respiration rate only. You can use any variable. As I mentioned earlier, this is my signal. This is actual respiration signal. Like I am taking only 512 components only. This is like this is signal is 1024, like it's 2 power 10. As I mentioned earlier, you should maintain the signal length as 2 power m. So this is how we will define the FFT. We will initiate FFT algorithm in Arduino. Like this is just serial begin only. To use the FFT we need to write one variable FFT equal to Arduino FFT, and in that FFT you need to give that a real part, imaginary part, and number of samples, and exponent in the sense it will return the value of log of something base 2. Like here it's my signal length is 1024, it will give exponent of 1024, it will give it's 10. Okay, these are the variables which we need to give input to the FFT command. So that FFT forward means it's a FFT reverse means inverse FFT. After completion of FFT we need to uh, change them to complex to magnitude. So for that we need to use this command, complex to magnitude VReal VImagine and number of samples. After getting here, I need to calculate the maximum frequency component within my K1 and K2. As I mentioned earlier, that formula f into n into by fs. If you substitute two values of f, you will get range. Like for a number n equal to 1024 and fs equal to fs equal to 25 Hz, my k1 is 1 and my k2 equal to 20, like it's around 15, I can maintain 20. Here in between this range I will find the maximum frequency component, and I will store here max 1, and I will find that corresponding frequency. I will find respiration rate by using that corresponding frequency. After finding that, as I meant, to compute inverse FFT, I need to make the all other frequency components 0, so that I will get only respiration signal. Here what I am doing, that same, I am maintaining all other components 0, and here BPM is, I mentioned earlier, breaths per minute. This we have I computed this max 1 equal to k now. To you want to change that k to frequency, but we will use this formula 60 into, no, not 60, max 1 into fs by 1024, like basically k into fs by capital N. Here capital N equal 1024. I want to compute the number of cycles per second, no, per minute. So I am just multiplying it with 60, so that I will get respiration rate. After getting, this is my BPM is respiration rate. After getting respiration rate, I am using IFFT. The basic difference between FFT and IFFT is just FFT reverse only. If you use FFT reverse, you will get IFFT. And same, I am again multiplying, I am again changing it like complex to imaginary. So this is I want to plot. If you plot, as I shown this figure earlier, so let's do not plot this, but we will see the respiration rate now. Okay. mm, Here I am printing respiration rate and what is the coefficient at which I am getting that particular frequency. So it will take some time. mm, Now I will show you the value in serial monitor. The first value is the respiration rate and second value is the maximum frequency and the coefficient at which we are getting that frequency. Okay. Oh, it's taking time. Like my laptop is a bit slow. Okay, please give me a few seconds. uh, this actually these are all the first value is only correct value, like the respiration rate is 16 breaths per minute, and we are getting that particular component at 11th coefficient. Okay. mm, if you plot this. Okay. Now our job is to find the respiration rate by using original respiration signal. Then only we can compare. No, so let's find after finding the respiration rate by using original signal, then we'll do the same experiment in the MATLAB and we'll compare our results again. So here this is my own respiration signal, and here just as mentioned earlier only, this is the FFT algorithms code. Like these are the basically functions you need to use FFT. FFT is the inbuilt program in Arduino only. So after that you will find the maximum coefficient, and then you will find the respiration rate by using that coefficient. Here frequency sampling frequency is 10. Oh, okay. Here I am just, it will give just, it will give the free FFT of the respiration signal only respiration. Now we'll find respiration rate. After that we will run the same code by using MATLAB, so that we will compare better in a better way. Okay. Come on. Yes. See, 15, 16 only. Respiration rate is 16. So this is the only respiration rate, and before code is like we have PPG plus respiration, but we are able to separate the respiration signal by using uh, that respiration frequency range. Now we will perform the same experiment by using MATLAB. This is the, here I will okay, same signal only, but I will do, I'm running. See, here first here again I will do by using DFT. I'm just comparing by using, this is DFT by matrix method. Then I am finding by using direct FFT command. Okay, this is the this is the Fourier transform by using DFT matrix method. This is Fourier transform by using FFT, direct FFT command. They are more or less, because here size is somewhat less. No, here 750 samples only I took. Like if size is very larger and larger, like this method is won't efficient, this method only efficient. This is the effect of the original respiration signal. Okay, and then this is the respiration signal from the inverse FFT, but this is the actual FFT. But if you observe clearly, but I just find I am just finding the maximum coefficient by using same method only. That but I am getting here results is first respiration rate is 18 by using FFT, by using that signal PPG plus respiration. If I use the only respiration signal, I am getting 16%. 16. The difference is 2 by 16. So error is approximately 11%. Okay, let us understand the code. Here this is my actual PPG plus respiration signal. This is only respiration. Here I am just finding here my sampling frequency is 25. Actually here length equal to 750. 750 means like it's 30 seconds data. I'm just finding the DFT of 750 DFT. This is actually I'm performing moving average. Then I'm computing the DFT matrix, and I'm here DFT matrix, and here I am just finding the DFT, discrete Fourier transform, by multiplying those. And after that I am just finding by using FFT command. This is by using just FFT command. Here FFT is the inbuilt command. Then I am plotting here. Then I am taking, as we know that if respiration range is 1 to coefficient range 1 to 15, so I am finding the maximum value in between, and I am finding respiration rate. After that I am making all the other components 0 so that I can compute inverse FFT. Now uh, here I am finding the FFT of the respiration signal only. I am finding the maximum value, and here just I am multiplying. I am just using the formulas to get the respiration frequency. Okay, original. So if we observe, they both are, this is 18, this is 16. Okay, this is how we'll done with today's experiment. So conclusion: respiration by using FFT of PPG plus respiration signal by Arduino is 16 breaths per minute. Respiration rate by using FFT only respiration signal 16 only. Respiration rate by using FFT of only respiration signal in MATLAB is only respiration in MATLAB is 16 only, but by using FFT is 18. So error is this 11.1 11.11. Okay.